Welcome to the Wily Wallabies final project presentation. Our robot is a self-righting robot that is inspired by saddleback tortoiseshells. A little bit for our project overview. We have modified our robot to have the ability to self-right itself when turned over. This is inspired by the shell shape and head movement of the saddleback Galapagos tortoise. We have fabricated a shell for our robot, as well as implemented an extending neck that imitates the motion of tortoises when self-righting. The self-righting ability will improve the reliability of robots that travel on uneven terrain or encounter unexpected obstacles while we're in use. A summary of our objectives are that we are modeling a Galapagos turtle and exploring the benefits of a saddleback-shaped shell combined with neck extension and its effects on self-righting versus that of a domed shell tortoise. The hypothesis of the paper we've cited deals with the self-righting, or explains that self-righting depends on shell morphology, body flexibility, and body shape. Our hypothesis for our robot is that a modified back shape and extending neck will improve the robot's ability to self-right. And we view our biological translation of the animal's ability to tell if it's flipped over with an accelerometer that senses the robot's orientation. A long neck will extend to tip itself back over, which will be replaced by a rotating actuator. Flailing legs and generating sideways momentum will be done by flailing the kamigami legs or just operating the legs in general. Now I will go over our discovery decomposition. First, the background hypothesis. There are two main shell morphologies, which are saddlebacked and domed. Fast overturning of a robot or of a tortoise reduces the chance of fatality. The energy required to self-right is greater than the energy deficit. And self-righting is a fitness-related trait for tortoises. Next, the methods. 3D shell reconstructions of 89 Galapagos giant tortoises were scanned based off of 3 domed species and 2 saddleback species. They evaluated the center of mass, and they compared neck and carapace height for domed and saddleback tortoises. Next, the results. Saddleback tortoises have a longer neck than domed. There is no difference in self-righting potential between males and females, and it was found to be related to the energy deficit requirement, body mass, and neck length. Saddlebacks have more difficulty in righting than domed tortoises. Now the results. Now the conclusion. Results support the hypothesis that tortoises with a saddleback shell shape may use their neck to create a momentum to self-right. Lower self-righting potential in saddlebacks as compared to domed tortoises based on the shell shape, and a higher energy input is required to self-right through longer necks and longer extensions of the neck. This leaves us with the test hypothesis, which is that the shape, flexibility, neck length, and energy deficit required to overturn are interdependent and have quantifiable relations.
All right, so for the analogy check, we compared the Galapagos tortoises to our robot, first with the aspect of behavior in mind, and we note that they both travel over similar surfaces and have the ability to self-right when flipped on their back. As for the structural components, both the animal and our robot use a carapace. As for the neck, we have a stationary piece of acrylic as opposed to an extending actuator with 3 degrees of freedom. Also similar are the functional mechanisms, such as pushing the head on the ground, the extension and actuation of the neck, and the bobbing of the feet. Also, the characteristics and specifications, such as the height ratio of neck length versus the shell height are similar, use of the neck to create momentum, and the rocking motion to achieve self-rightedness are all similar characteristics. As for the performance criteria, both the robot and the turtle self-right and flipped on their back. The neck provides momentum to the whole turtle by pressing against the ground using the servo in our robot, and similar behavior noted in the actual tortoise. As for the feet movement, they rock the turtle body, which is seen in our robot as well with control. Also, one of the similar constraints is the center of mass, which is important for the turtle to self-right, which is also contained in our robots. So as for the servo motor and neck design, One of the key features was that the head of the tortoise has a relatively rough skin. We tried to mimic that with the high friction latex material. Our electronic setup consists of 4 AA's to power the servo and an Arduino Uno, an accelerometer, and a 9-volt battery to power the Arduino, not shown in picture. The servo essentially moves back and forth when the accelerometer passes a certain z-axis value. When it is back within the range, the servo returns to its original position. As for when the robot is upside down, the motion continues back and forth in a 180-degree sweep, and once it's right side up, the servo stops.
Here we can see a video of the accelerometer being flipped over and powering the servo. This is just so we can detect when the robot is upside down and tell the servo to drive. Next, we're going to talk about some of the shell shapes. We had 2 different types of shells that we tested. On the left in the green, you can see depicted a saddleback shell. This is a little flatter and a little wider with a larger opening in the front. This is to allow the actuator to drive the neck. On the right, you can see the dome shell. This has a more curved shape and is a little taller. This gives us a higher center of mass and allows us to get the rocking that we need while running the robot. The third design we did test is the original robot without any of the shell modifications. Next, we can see the comparison between the shells that we had created and the actual tortoises that we modeled them after. Again, on the left is the dome shell, on the right is the saddleback. On the top will be a dome tortoise, and on the bottom will be a saddleback tortoise. Next, for experimentation, we had to purchase and integrate a servo motor, accelerometer, and our custom 3D printed shells. These would all be attached onto our robot to see how the self-righting would be affected. Next, we developed statistical tools. This would help us see the results in a more clear way. The next thing we did was 3 different tests. We tested on different angled surfaces just to see how that would affect our self-righting ability. We tested on 3 different types of surfaces to see if the friction coefficient would be different between these. And we tested on a constant surface. This would just be the reliability of the robot to ensure that it could flip over multiple times.
So next for our testing, we tested all of our designs attached to the Kamigami robot, which isolates the variables we wish to test. And then we turn the robots onto their shells like they would be flipped over at the specified incline or terrain, and then flail the legs to generate the momentum, like was mentioned. And then we don't touch the robot while it's in this phase to ensure that self-righting is not affected by outside parameters. And then we also test reliability for both our mechanical and sensing systems by doing a number of flips and measuring the percent of which that were successful. So for our first test, we have our angle test, and essentially we tested our domed with the neck, or domed without the neck, which was addressed in the paper and is more similar to the wildlife species. And then the saddleback also with the neck, which is similar to an actual species in the original Kamigami robot. We found that the domed and the saddleback with the neck were the only ones to be able to flip over, but then we also found that the angle did not help it actually flip over at all. And you can kind of see this in the video shown. It's actually just pushing it off of that surface and getting it stuck in the crevice instead of actually helping it, which was an interesting finding for us. The next test we did is a surface test. So we tested first a flat surface, and also on grass we can have more friction. It's also more similar to the tortoise's environment. We can see with the domed with the neck shown on the top right corner, we saw that it was able to flip over after a number of attempts because the center of mass is pretty unstable. And then for the saddleback, we saw that it did not work in the grass because the feet were getting stuck in the grassy soil material, which was an interesting finding for us. And then also on the concrete, our saddleback was able to work. So our findings, similar to the last test, found the domed and saddleback with the neck were the only ones to be successful. Our last test that we did was a reliability test. We think this is the most important. We did it on a smooth table surface, no propping angle, and 5 trials. Well, we found that the domed was the highest performing in this category with 100% effectiveness over 5 trials. The domed without the neck, similar to the wildlife species, did not work at all. And our saddleback seemed to have very similar results to the domed with the neck, with 80% success rate. And the original Kamigami did not flip over at all. So here's a discussion of some of our test results. For our angle test, we found that the angle did not assist in the writing ability, and it did not help significantly improve the writing. And for a surface test, the domed and saddlebacks can both self-write on flat ground, but were unable to because of their feet getting stuck in the grass/uneven terrain. We also found that the results of the reliability test showed that the dome neck performed slightly better, but the saddleback also performed nearly as well. And this proves our hypothesis that the neck of the tortoise significantly improves the ability to self-write, which is a really important finding. Interestingly, the dome shell takes more rolling around to self-write because of a more unstable center of mass. Although it does eventually self-write, the saddleback is slightly less reliable, but has a much more controlled self-writing. So it takes much less time to self-write, and we'll be able to see this in the next slide from Courtney.
So these two videos demonstrate the full motion of both tortoise shells. So these videos demonstrate the robots walking, getting knocked over, and eventually self-righting. And after watching these videos, you can notice how much longer the dome shell takes because of its unstable center of mass.
Next is the saddleback video.
So a potential application for the modifications that we've made to our robot is that robots are used on some large campuses and can autonomously deliver products from point A to point B. However, when they're knocked over, they're unable to deliver the packages. So if our mechanism was integrated into these robots, they would be able to self-write and can deliver the products. So the significance of the work we've done is that it'll allow us to better understand the relationship between tortoise morphology and limb and neck movement when used to assist in self-writing. Additionally, our improvements will allow robots to be able to traverse unstable terrain and negate the risk of overturning and becoming immobilized and remaining inoperable. And lastly, we believe that this is an efficient method of helping robots improve their mobility while keeping weight, computational operations, and power consumptions requirements to a minimum. Thank you.